So today I will talk about electrical resistivity tomography that we use as a monitoring tool to monitor hydrological processes in the subsurface and mostly at the field scale or the site scale. So hopefully it will still be of interest for you that I think work more at the lab scale, but everything that I will present are transferable very easily from the site scale to the lab scale. So first of all, so I will introduce what I mean by electrical resistivity tomography, so essentially it's a method very similar to medical imagery, where we try to sense the electrical resistivity distribution in the subsurface using a set of electrodes. So usually we have 4 electrodes, and we inject current between 2 electrodes and measure voltage between 2 other electrodes. And thanks to Ohm's law, we're able to have access to the resistance, which multiplied by a geometric factor gives us the electrical resistivity, which in a sense is the resistance of the ground to passing electrical current, and it's basically the opposite of electrical conductivity. So usually to be able to build up models of the resistivity, we multiply. Well, we measure along a set of electrodes. So we repeat these measurements either along a line of electrodes or a grid of electrodes if we want 2D or 3D imaging capabilities. And the resistivity itself is sensitive to mostly geological variations, but also changes in groundwater saturation or moisture content, and also temperature. And it's scalable, which means that we can focus on scales of centimeters in the lab, for example, or kilometers in the field. The technique has been increasingly used in side-scale investigation surveys, but more recently it's also been used for monitoring aspects. So by repeating measurements and installing the electrodes and the system permanently on some monitoring sites. So at BGS, for instance, we've developed an instrument and a technology using electrical resistivity tomography, and what it's called the PRIME technology. So essentially, it's composed of resistivity meter, so the PRIME instrument, which pilots a set of electrodes, which are then acquiring the data on a scheduled basis, if you like, and thanks to telemetry, we can communicate to the instrument, which is installed at specific sites, and then we can acquire the data, and thanks to doing some inversion and processing on the data, we can access and generate resistivity images and models of the subsurface, and then look at the temporal variation, and ultimately, thanks to some property relationship linking resistivity and other parameters such as moisture content, we're then able to access models of the moisture content through time at specific sites. So we'll illustrate this technology in a couple of case studies. So case studies from our recent work in the team. First, a case study is reservoir dam monitoring. So here we installed a system at Nurse Dam, which was constructed a long time ago, and only little is now known about the structure and the design of the core of the dam. But seepage and leakage is identified at the surface of the dam, is obviously of concern for the reservoir owner. So we apply this technology to provide more information and to understand the leak sources and potential seepage pathways through the dam, and discriminate between rainwater and leakage from the reservoir. So we spread 256 electrodes in this case as a grid over the surface of the dam, which are basically laid out in lines parallel to the dam orientation, if you like. And you can see one of these lines being buried for more safety as the installation is permanent and we acquire data on a daily basis. Here the instrument with solar panel feeding the batteries, and the PRIME instrument itself and the router, which enables the remote communication with the system. And then here first results as a baseline, so showing the distribution of the resistivity in terms of 3D model of the dam, showing the distribution of the resistivity, which first shows that the dam is quite heterogeneous in terms of resistivity, which points to variation in the material composition at the surface of the dam, but also changes in the moisture content, as we can see that the area of seepage identified at the surface of the dam shows up as a conductive area, so blue color here that we can see. And if we extract a volume of iso resistivity, so defining the lower resistivities in the model, we can start to investigate the areas associated with this seepage. We also have access to some borehole information that are also displayed here to be able to guide a little bit the interpretation on the resistivity distribution on this model. But now we can also, using this baseline, we can compare and look at the changes in resistivity through time. So this animation will first show a fly through the resistivity model put in perspective with the dam, but then we'll show the changes in resistivity expressed as calculated from the baseline, and we'll highlight the decrease in resistivity, which are associated to increase in moisture content. So first of all, we have this fly through, so we're able to identify slightly more easily the changes in resistivity, and then we'll start to show the changes in resistivity, and highlighting only, as I said, the decrease, the area with the most pronounced decrease in resistivity. So we can see that two areas show up here in this model, and then we are able to look at these changes in more detail. And for instance, you can see in the right corner here that we highlighted 4 areas of interest from which we're able to extract the resistivity values and plot them against additional data, such as the rainfall data here at the bottom, or the reservoir level itself, and some flow data coming from a V-notch at one point location in the dam. And so the whole purpose of this visualization is to try and discriminate between the areas which are mostly affected by rainwater infiltration and areas which are mostly affected by seepage from the reservoir water, if you like. So and on this side we have 4 different points of view of the model as we go through time, and we can start to see, for instance, here that at some point when the reservoir level is high, that we've got these lateral wetting front, if you like, that are linked to seepage pathways, whereas some superficial areas are more affected by the rainwater infiltration. So this was for this case study about reservoir dam. Now we'll switch to another case study on natural landslide. So here it's an example of tropical mountainous region where we equipped a slope which is prone to landslide on a seasonal basis, mostly linked to the monsoon in this case. So the moisture is the main driver of slope failure here, and directly threatens a community living at the bottom of the slope. So the monitoring objective in this case was to study the hydraulic processes inside the slope to be able to delineate or better inform early warning systems already operational, but we were hoping to be able to better understand and to try and inform landslide modeling initiatives. So in this case, same kind of animation here, just different color scale. Here showing the resistivity distribution within the slope. And we can see that in this case, we can interpret the contrast in resistivity linked to the weathering intensity, because we are in a tropical region. So there's the soil is intensively weathered. And then we've got, changes in resistivity as we go in deeper areas of the subsurface. So one is linked with the water table, which, decreased the resistivity quite significantly, but also at the bottom of the slope where we had a landslide event in the past and the soil layer has been removed. We directly have outcropping weathered gneiss that have, a resistivity signature here that is different than that of the soil. And then again, we're able to look at the changes in resistivity. Again, only here highlighting the decrease in resistivity, which are associated to increase in moisture content. And we show this as we go through the onset of the monsoon season. And we start to see that at the beginning of the monsoon season, the first few rainfall events start to wet the shallow layer of the surface. And then as we go through the peak of the monsoon, we start to affect the whole model and the whole slope. And then as we go through the beginning of the dry season, everything dries up. But since we compare everything to the beginning of the monsoon season, it starts to be slightly difficult to visualize changes in the most interesting part of the season. So we can also look at the changes from a different baseline. So in this case, at the peak of the monsoon, and we'll start to look here not only at the decrease in resistivity, but also the increase in resistivity, which are linked to drying processes. So red here is pretty simple. Red is drying and blue is wetting. And as we go through these three main rainfall events in the monsoon season, we'll start to see these wetting and drying phases that the slope experience. So first event, then it dries up, then a second at the peak of the monsoon. And then as we go through the dry season, we start to see progressively the whole slope, which dries up. So now we can also visualize this slightly differently. Here I show an example of using the time series and the resistivity time series and using some time series clustering to be able to identify rapidly some zones of interest, and then looking again at the changes of these zones against other information such as the rainfall or moisture as measured in boreholes. Now, I mentioned at the beginning of this talk that we're also able to translate these changes in resistivity in terms of moisture content. So this is a last example, very quick one, from an observatory in the UK, where we've been able, because the geology in this case is pretty homogeneous, we've been able to calibrate some relationships between resistivity and moisture content with measurement on soil samples, which helps us to directly visualize the changes in resistivity in terms of gravimetric moisture content. So in this animation, we first see the distribution of the resistivity, but then the changes in resistivity are not showing up as changes in resistivity, if you like, but as changes in moisture in this case. So we start to see here at the top of the slope moisture buildups, which are directly expressed and quantified in terms of moisture and not only in terms of resistivity. So that's it for me. I mean, I hit the summary. So basically, I've tried to illustrate how electrical resistivity tomography can be used to provide high resolution images of the subsurface here at the site scale, but it can be transferred and it's being transferred at the lab scale for lab experiment, for instance. ERT monitoring is suitable to investigate hydrological processes. I showed dam leakage or moisture buildups in landslides, but several other applications include monitoring of thermal processes, permafrost thawing, aquifer contamination, or seawater intrusion, and so on. So thanks very much for listening, and yeah, thank you.